looks like there are no questions. So now we'll have a talk by the winning team of the Visual Dialog Challenge 2019, MReal-BDAI.
I'm sorry. Okay. So good afternoon, everyone. I'm Yulin Yu from Renmin University of China. Today I represent our team, MReal-BDAI, to introduce our winner resolution in Real Dialog Challenge. We first thank the community for organizing this great workshop and challenge. So first, I will quickly give an overview of the Real Dialog test and this year's challenge. So the main difference between Real Dialog and Real Question Answering is the dialog history. Therefore, how to utilize the dialog history is one of the key challenges in Real Dialog. And the Real Dialog model is evaluated using retrieval metrics. We have two types of answer annotations. For sparse annotations, only one answer in the candidate set is annotated as the ground truth answer. And for the dense annotations, several annotators are invited to judge whether the answer is relevant to the question. The evaluation metric on dense annotations is NDCG, which is also used to pick winners in this year's challenge. So there is some differences in this year's challenge. During the training stage, we are provided with extra subset of dense annotations. Specifically, 10% of the questions from the validation set are annotated with the relevant stores by 5 human annotators. For the training set, only 0.16 of the questions are annotated by 2 human annotators. Here comes the second challenge in this year's competition: how to effectively use the dense annotations. Next, I will introduce the details of our winner solution. So recall that we have stated 2 challenges: how to model the dialog history and how to utilize the dense annotations. For dialog history, we only use it for visual reasoning to obtain the correct visual attention. We found that using the history encoding in the question answering part will lead to the overfitting to the sparse annotations. For utilizing both the sparse and dense annotations, we proposed a simple but effective 2-stage training paradigm with the generalized cross-entropy loss. Here is an overview of our encoder-decoder architecture. We modified the recursive visual attention model for encoding the image, question, and history. The details of the recursive visual attention can be found in our this year's CVPR paper. In summary, we expect the dialog agent to perform explicit reasoning as like humans, and we struck the dialog history as the recursive tree. We use the discriminative decoder to calculate the similarity between the input encoding and the answer decoding. The main difference between the modified recursive visual attention and the original one are as follows. First, we remove the history encoding from the question answering part. We found that the history encoding encouraged the models to pick long answers. One possible reason is that the attendance of history encoding will enhance the language feature but weaken the visual feature, which leads to the overfitting to the sparse annotations. This modification will improve NDCG by nearly 3 points. Second, we designed the multimodal encodings by additional embedding layers. This structure is proposed to deal with different types of questions and leads to approximately 1 point improvement. More importantly, this structure is helpful in model ensemble by using different numbers of the heads, which results in additional 2 points improvement. Here is an overview of our tips. In this challenge, we simply fuse the visual feature and question feature by element-wise multiplication and concatenate the fused feature in the joint embedding. In addition, we add the spatial features by concatenating the coordinates of bounding boxes with the visual feature. And for the challenge about how to use the dense relevance scores annotations, we apply a two-stage training paradigm. The cross-entropy loss is widely used for the descriptive settings, and we generalize the loss by using different sources of labels. The first stage is the same as previous works using the one-hot ground truth answer. This stage can be regarded as learning how to reason from multimodal data. After that, we fine-tune the model using the limited number of dense relevance score annotation. This process can be regarded as how to answer like human. We find that such a fine-tuning stage finally improved the NDCG by over 10 points. Here are the implementation details of our solution. For the visual feature, we use the recent bottom-up features. During the training stage, we first pre-trained the model using only sparse annotations for 10 airports, and then fine-tune the model using the dense annotations for 2 airports. We also apply an ensemble strategy with different numbers of mounted head encodings. Last, I will analyze the experimental results and think about the real dialogue task. So here is an example about the language bias. The leftmost table is the dense annotation. The middle one is the results trained with only the sparse ground truth answers. The rightmost one is the results trained using sparse and dense annotations. We found that when training with only the sparse annotations, some candidate options obtain high ranks because these options have the same phrase in the question, for example, on the wall. This example shows that the model trained with only sparse annotations may tend to repeat the same words. And in this example, some unrelated options are partially correct because they have the word no. The model trained with only sparse annotations fail to distinguish these answers with the correct answers. And here's a very interesting and important example. The question is, how old does he look? The annotators have different ideas about the answer. Some annotators think that it is hard to answer these questions, but others are trying to estimate the man's age. Although the model trained with only sparse annotations achieves low NDCG, but we cannot say that the model is not good because it is just not smart enough to give the safe answers. We further analyzed the difference between the sparse and dense annotations. We found that not all the ground truth answers are annotated with high relevance scores. The reason may be that the annotators were not provided with the ground truth answers when annotating. Therefore, the annotators tend to select the safe options, which leads to the inconsistency between the sparse and dense annotations. Furthermore, we think about why our two-stage training works. The reason may be that the model can learn to give safe answers like the annotators by fine-tuning on the dense annotations. We also found that by this training paradigm, even the VQA-like model can also achieve competitive results without using any dialogue history. There remains a question whether the language bias in the dense annotations or whether we didn't utilize the history well enough. Finally, we have some suggestions on the future of the real dialogue task. Real dialogue is a very good task for reasoning from both vision and language, especially for the dialogue history. Our proposed recursive visual attention is just one small step in the real reasoning. Since there exists the inconsistency between the sparse and dense annotations, maybe the annotators can be provided with the ground truth answers for further annotations to see whether the inconsistency hurts the utilization of the dialogue history. That's the end of our presentation. If you are interested in our work on explicit reasoning in Dialog, please take note of the oral and poster information of our this year's CVPR paper. Thank you for your attention.
Are there any questions for the winning talk of this year? If there aren't any talks, if there aren't any questions, let's thank the speaker again.
Thank you.